a changing magnetic field cutting across a wire induces an EMF. So I'm changing my magnetic field by moving the magnet, but I could do the reverse. I could actually move the coil into the magnet, and it's a relative motion. The effect is the same. So how do we then harness this energy? Well, what we've got here is a Faraday torch, not battery power. There's no battery here. And what we've got coils similar to that one. And inside it, there's a magnet that moves. And notice that as you shake it, turn it on. As you shake it, you could see the glow. You could see it turning on and off. And that's because as the bar magnet cuts across the magnetic field, there's a change in magnetic field that induces an EMF. Obviously, that's connected to an LED and that lights up. But how do we use that in a power station? So for your GCSE spec, you'll need to know different types of generators. We've got the alternator and we've got the dynamo. Alternator starts with A, that forms AC. Dynamo starts with D, that forms DC, okay? Over here, how do I now recognize an alternator from a dynamo? Well, a dynamo has got a split ring commutator. So again, I've got my galvanometer here that can measure very small changes in voltage. And notice what happens as I spin this, just making sure these brushes make contact. We got a deflection. Spinning to the right gives me a deflection to the left, and reverse that, the deflection is on the other side. If my galvanometer is only moving in one way, then that means the current is only flowing one way. That's a DC. So a dynamo gives you DC. So this, in effect, is a dynamo, not an alternator. All right. So this is how we then use this in a power station, except that in a power station, they may use an alternator where you're getting positive and negative. There you go. Move it faster. The rate of change of flux is higher, so you get higher voltage, hence the deflection is more. The other way, same principle. There you go. Thank you. We've done this too many times now. So a changing magnetic field cuts across a wire and it gives you an induced EMF. But this demonstration is about showing to you that we can use a changing magnetic field without having a bar magnet. And how do we do that? Well, we use an AC. And let's see how this one works. So I've got a similar setup here, except that this one's got a lot more turns. So it's going to pick up the induced EMF more. And I've also got a microammeter, very sensitive, 10 to the power minus 6 amps. This one over here is milliamps. So divided by 1,000, divided by 1,000,000. And let's see what happens. As you can see, there's no external circuit. There's no battery powered here. And I'm going to leave it like this. I would now use this little device here, which is just like a solenoid, an electromagnet. But instead of connecting that to a DC, I'm going to connect that to an AC. If we plug this directly onto the mains, the 50 hertz frequency is too much for a change. So we connected that to a signal generator that allows us to change the frequency. And let's see what happens. So again, as you can see, when I turn this on, there's a magnetic field around here, not cutting across, like in a transformer, nothing. But watch what happens when I insert it here. Ooh, look at this. I'm getting an induced EMF, positive, negative, positive, negative. Why positive and negative? The current is going one way, the other way, but there's no magnets here. However, the magnetic field is constantly changing, and you can see that's connected to an AC. That's connected to an AC. But this is a beautiful kit that shows to you that you don't need a change in magnetic field just from a ball magnet. You could use an AC, and that's what a transformer uses.